Alright, silly people, here's the situation. We're going to be finding the momentum space wave function for the free particle. So here is the procedure for finding a momentum space wave function. Here is the wave function that we are actually going from in position space, the one for the free particle. Uh, and we're told to leave it in terms of this guy, this phi of k, which is just a complex function that is entirely dependent on the initial position space wave function that you're starting with um, after you let the particle become a free particle, which is why it's totally fine to leave it in terms of this as we go. So let's just do it. So then the momentum space wave function for the free particle, combining our equations, we'll get a factor of 1 over 2 pi, square root h bar on the bottom as well, h bar coming from the 5p of t thing. And I've got the integral from minus infinity to infinity, dx, of integral of minus infinity to infinity dk, phi of k e to the I kx minus omega t minus px over h bar. And that's it. Now there's nothing saying that we can't reorder the integrals, so we're going to do that because the x integral is actually possible since we know what everything that depends on x is. The only thing we don't know what depends on k is phi of k, so we can just pull it out. So reordering the integrals makes it look like integral from minus infinity to infinity of dk phi of k, and then the e to the I omega t stuff doesn't depend on x either, but then inside the x integral we still have the e to the I kx minus px over h bar. And I'll even factor out an x from the parentheses up there just to show off the fact that this integral, you don't really do it classically. The result of it is a delta function. Whenever you have bounds at minus infinity and positive infinity, the result of an integral like this gives you a delta function of whatever is attached to the e to the ix. In this case, it's k minus p over h bar. So we've got 1 over 2 pi root h bar. We've got the integral over k of phi of k e to the minus I omega t. And then it's 2 pi times the delta function k minus p over h bar. Now that we have a delta function, we can actually just do the k integral now. Canceling out 2 pi's, the integral becomes just phi of p over h bar, and e. I'm going to fully expand what the exponent is at this point since omega depends on k, but we're going to be plugging in p over h bar for k is what's going to happen. So it's minus it h bar over 2m, and then p over h bar squared. Okay, in other words, it's 1 over h bar phi of p over h bar e to the minus it p squared over 2m h bar is all she wrote, right? The square modulus of this doesn't depend on time because the only place where time dependence shows up is in a complex exponential. So when we take the square modulus, it'll just go away. And then we've got 1 over h bar times the square modulus of the the initial momentum distribution. But okay, yeah. So that's that. It doesn't depend on time. The way that you can parse this is, if you set a particle free, um, after whatever initial conditions, um, if you try to measure the momentum again while the particle is still free, um, it doesn't depend on time what distribution function you will get for your momentum. You're going to find the same percent chance of any momentum you're measuring given this, since the particle isn't interacting with any sort of potential as it's going, since it's free. Yeah. So, all right.